just we want to let everyone knows that the meeting would be recorded. So just that one. So if everyone is happy, so we are recording the meeting. Yeah.
Thanks so much. And feel free to shoot in the questions while I'm talking as well. So, yeah. So the presentation will have 3 sections, just a brief introduction, motivation, and then the contributions of the work, where we introduce a new distance metric for mixed data. I'll talk through the structure of the clustering method, and then sort of an adjunct procedure to select centers automatically and remove need for manual input in the method. The paper, which we submitted to STM 2021, but we're still waiting to hear back, but it is available on arXiv, and there's an associated Python package which is available on PyPy. I think I have a link to that at the end. So my work focuses on sort of unsupervised learning applications in other learning settings, like supervised learning, for example. And sort of the motivation of it is that developing fast and flexible clustering algorithms is really central to making it a feasible part of like bigger sort of machine learning pipelines or other sort of data pipelines, basically. So just an application or an example of applications which use clustering methods in other learning domains, like cluster-based resampling algorithms are really commonly used in imbalanced data and multi-class classification settings. Weakly supervised learning settings like semi-supervised learning and multiple instance learning use clustering methods to propagate labels throughout data. And even within supervised learning algorithms like decision trees, clustering has been used to improve like getting splitting criterions in decision tree algorithms such as CART. And these application domains sort of regularly contain data sets which can sometimes be challenging for the majority of popular clustering methods. So when we think about these application domains, they sort of force us to consider what kind of clustering algorithm we need and what we need it to do. And I think there's kind of two strands that we need to consider here. So firstly, we need to think about the type of clusters that we want a clustering algorithm to detect. So for example, in resampling algorithms using clustering methods there, we need to be able to detect heterogeneous clusters in terms of their shape, their size, and their density. And for sort of more exploratory work, needing the number of clusters in advance can be a hindrance. So we'd want to be able to develop a clustering algorithm where we don't need to know K in advance or specify K in advance. For the algorithm which we use to actually detect these clusters, right, we need it to be consistent, adaptive, and quick are sort of the 3 criteria which we set out for ourselves. And consistency meaning that the algorithm isn't sensitive to initialization or random initialization points. Adaptive meaning that the user has control over different outputs and can vary parameters to change the outputs that they get. And quick meaning that the algorithm would run, sort of being generous to ourselves, I guess, at least subquadratic in complexity. So for our approach, we take as a starting point the density peak finding clustering algorithm, which was introduced by Rodriguez and Lau in 2014. I'm going to refer to it from now on as DPC, but when I say DPC, I mean density peak finding clustering. And DPC is an intuitive clustering method based on a really simple idea. The idea is that cluster centers are points which are surrounded by lower local density, and these points should be at a large distance from points which have higher local density. So if we consider like a toy example here, which I have on the bottom, our eye kind of forces us to see 2 clusters here, a large cluster in the sort of bottom right of the figure and a smaller cluster in the top left. If we use the color of the points to represent the local density of the instances, and I'll come back later to how that's actually calculated, we see that the sort of central instances have higher local density than points on the edge of the clusters. If we represent the other quantity which is of interest in the DPC method, the distance from each point to a neighbor of higher local density, by the size of the point, we see that various values here are suggested as potential cluster centers. We have definitely 2 big ones here in the top left of the large cluster and in the center of the smaller cluster, and then sort of around the right edge of the smaller cluster, or of the larger cluster, sorry, excuse me, would be proposed as centers. But the question sort of arises, okay, well, how do we choose between those, and how many of these should we actually choose? Well, in the original DPC framework, the authors propose plotting the instances on a scatter, basically, of local density, the computation of local density, and distance. This is the distance to the nearest neighbor of higher local density. And we can see the extreme values here selected in the graph, or in the top right of the graph, the most extreme point here, and then sort of further points as you move down. If we select, sort of manually select the proposed cluster centers, I'm going to choose the one here on the top right and the next one here in green as the centers. These are the ones that I'm going to use for my clustering. So if I transpose these then back onto the original data, we see that they seem to belong sort of to the clusters which are intuitively apparent from just looking at the data or the visualization here. And we can see that we have selected the largest point here in the large cluster, and then the central point in the smaller cluster here. With the cluster centers selected now, we need to actually consider, okay, well, how can we assign instances to clusters? And this is a really key idea in the DPC method, and it's something which we're going to use later on for our approach, where what we do is we essentially assign each non-center point to the same cluster as its nearest neighbor of higher local density. Okay, so this is a distinction from other like partitional clustering algorithms like k-means, where you assign points to clusters based on the distance to the center. Here, the assignment has actually sort of a more agglomerative structure, right? What we're doing is we assign each point to the same cluster as its nearest neighbor of higher local density. So what you see is you sort of get this sort of like tree structure of assignment points. And what we can see is if we were to actually select a new center here, say we're to select this point as a center, this group of data points here is exactly the points which would be assigned to that cluster. The assignment strategy is actually predefined when we compute the density values of the points, right? So we can see that the clusters are essentially already defined by this top-down, or sorry, actually bottom-up assignment strategy of the instances. And that's a really central idea in the DPC method. It's something which we bring forward into our approach too. So this DPC approach is intuitive, definitely, and it's effective for some data sets, but it's limited in three main ways. The dissimilarity metric which they use is only applicable to numerical features. It's not really a hard issue to circumvent, but it is something which is limiting in the original paper. The density calculation for each instance in the original DPC work uses all of the data points. So actually computing the local density has quadratic complexity, it's ON squared, which doesn't make it feasible for larger n data sets. So we need to find a replacement way of computing the density. And the decision graph and center selection method is appealing, but it is a subjective process. And the example which we had is actually quite an easy example. Trying to interpret these decision graphs can actually be a difficult process, as well as taking time and effort from a user. So we want to maintain the effective parts of the DPC method, namely, the intuitive nature of the approach and the assignment strategy, but we want to adapt it and extend it in three main ways. So the first thing is that minor change, which I introduced here. So we introduced a new metric for mixed numerical and categorical attributes and ordinal attributes. We develop a new clustering method which combines this peak finding approach with connected components from graph community detection. And this improves detection of heterogeneous clusters and at the same time reduces the computational complexity of the density calculation. We also remove the need for manual input by developing an automatic approach for determining centers from the data. So first things first, I'll introduce just the metric which we use to deal with the mixed data types. So I kind of threw up like a stupid example here of the three different data types which we see. We have numbers, letters, and a vehicle type. So these are numerical data type, an ordinal data type, and a nominal data type. The numerical attributes are standardized by subtracting the mean and scaling by the standard deviation. In the work, we actually remove some of the outliers before doing that. We only consider the central data in computing the mean and the standard deviation, but it's sort of, it's not a major difference. The ordinal attributes get the same treatment. We first code them as integers and then perform the exact same treatment on them. So convert that to a numerical data point. And then for the categorical or nominal attributes, we one-hot encode them. So that means that for every category in the original categorical variable, we have a new binary 1-0 variable for the category. So you can see in the toy example, which I did here, we have truck, car, van, and boat. So for each of the 4 categories which we had, we now have a new variable. So we need to ensure that the contribution, though, of these categorical variables is not dominating over the numerical attributes, right? See here, if you think about it, we originally had three variables, one for numerical, one for ordinal, and one for nominal, whereas now the nominal attributes are actually dominating the data set which we have here. So to do that in the dissimilarity metric, which we introduce in the paper, we separate numerical and ordinal attributes from categorical attributes. So for the numerical and ordinal attributes, we just use the standard Euclidean norm, which is actually in the right-hand side of this distance formula. And for the nominal attributes, we also use Euclidean norm, but with weights for the one-hot encoded nominal attributes. So the 2 weights which we have are W here, which are matrix weights, and rho, which are scalar weights for the features. I'm going to introduce them now. So the W weights are information-based weights. So they're computed to incorporate the frequency of each category in the nominal attribute. So this information basically is useful in determining cluster membership, and it's used in a range of applications such as document retrieval, whereas the most common example of that would be TF-IDF, which is actually what some search engines used to use to match important documents with each other when you're doing a search. They use the frequency of the categories as some sort of guide to the information of their relevance with each other. But if you don't want to actually include any of that information, you can just set the W weights to be equal to 1. The rho weights need to be included though, and they're computed automatically. They're used to balance out the contribution of the one-hot encoded variables. So they ensure that the expected contribution of each variable is the same. And there's full details of the computation, the formula used to compute rho in the paper. But what we see is that the metric naturally balances the contribution of each variable with minimal computational load. It's not particularly difficult to compute, and you can actually apply the weights onto an array before using the clustering algorithm, and you can actually just use the standard Euclidean norm if you wanted to. So the benefit of this approach is that we actually achieve this balancing between nominal and numerical variables with minimal computational load. There's examples in the literature of sort of semi-parametric dissimilarity metrics, which are good and perform the exact same thing, but they take longer to compute, they're difficult to compute, and they slow down the clustering approach. So now that we have a dissimilarity metric, which is sort of sorted here, we could just plug and play into the original DPC framework. But the framework itself has its own issues. So if we think about an example here in the plot on the left, where we have 2 numerical features, and these are 2 horseshoe-shaped clusters. We have a blue cluster on the bottom, which is dense, and then a red cluster, which is less dense than the blue one. If we think about the decision graph that DPC would produce for something like this, what we see is that we won't actually select the correct centers. The first 2 most extreme points which are proposed are both belonging to the blue cluster, and the red center, which is down here, as the red cluster is sparser, we don't have as high a density value, and we wouldn't maybe select this point as a center. So what we see is that DPC actually struggles with clusters with varying density values because the decision graph process naturally favors high instances with higher local density. If we look at the graph here on the right, then what we've done here is actually selected the most extreme blue point as a center and the most extreme red point as a center. But even selecting centers from the true underlying clusters, we see that the assignment strategy fails to allocate the points correctly. The tail of the red cluster here is incorrectly assigned to the blue cluster. And the reason for this is that the assignment strategy is also based on density values. Remember, what we're doing is we're assigning to the same cluster as the nearest neighbor of higher local density. That leads to the misassignment of these points down here, right? So what we see is that the decision graph and the assignment process are both negatively affected by clusters with different density values in them. And if we actually take a sort of broader look at this, right, the actual process of the DPC method, the choice of getting centers from the decision graph is a difficult process, right? It's a subjective process. And I think that if these things weren't labeled in the colors, you could definitely have two people reasonably disagreeing about what the correct number of centers are. And that hurts reproducibility. The inbuilt subjectivity can be useful in some instances, but in other applications, it might not be something which you want. So what you would want is maybe an actual, rule which you can use to assess whether a point should be a center or should not be a center. So we have three main issues with the DPC framework: two density-based and one sort of more philosophical about the actual structure of the approach. So to tackle the first two issues, the density-based problems, what we try to do is better capture the underlying structure of the data. We see that when the data contains clusters with different densities, the decision graph and the assignment process struggle. So what we do is we use shared nearest neighbor graphs to determine areas in the data which should be considered separate. So in a shared nearest neighbor graph, the idea is to build a graph where every instance in the data set is a vertex, and there's an edge between two vertices if they're both within the k nearest neighbors of each other. Okay, this is a powerful approach for separating out different areas in the graph, and it was itself used as a standalone clustering method in Urtaz et al. And colleagues in 2003. It's kind of an interesting paper. They compute k nearest neighbor graphs or shared nearest neighbor graphs for varying values of k at different. They sort of consider those as different resolutions as they zoom in and zoom out and try to see what clusters or what components the graph actually throws up at you. This process is actually very effective at determining and detecting noise points, and can separate areas with different density out from each other, which is exactly what we're looking for here. So if we think about another toy example here, we have a toy data set with 1, 2, 3, 4, 5 clusters and maybe sort of a noise data around here. We can try to imagine what it would be like to actually apply density peak clustering here, how difficult the decision graph would be to interpret with that many clusters, or even try to imagine what applying k-means would be like here, or even a mixture model could be quite difficult to try to actually get the underlying clusters out from this data here. Whereas if we apply a shared nearest neighbor graph and try to split out different separated areas from each other, which are termed components, actually should have mentioned that, sorry. Connected components are the areas which are separated from each other when we compute the shared nearest neighbor graph. We see that the graph actually does the majority of the clustering work for us, yeah? We've separated this instance out from the noise points. We've got this cluster here and the cluster which is contained within it. And then we have this in the top left, which contains two clusters, but is separated out from the remainder of the data to make the method a lot easier. And the approach that we propose basically is to apply a peak finding method on each individual component set rather than on the whole data itself. And that's where the name of the method CPF comes from, component-wise peak finding method. So just to run through quickly what the actual structure of the algorithm is, we create the shared nearest neighbor graph with the parameter k. We remove the points with fewer incoming edges as outliers and create the component sets. And then on each component set, find capital K nearest neighbors, which we use to compute the density. So these two parameters, little k is used to create the component graphs, and big K is used to compute the density values. We find the distance from each instance to its nearest neighbor of higher density, select the centers, and then apply the assignment strategy as in the original DPC framework. What we see is that we don't, we can never assign a point to a cluster outside of its component set. So the idea is that if two instances are in separate components, that they're also in separate clusters. They shouldn't lie in the same cluster if they're considered in two different components. So if we imagine doing this, right, and we do this for each of the component sets, what do we end up with? Well, going back to the toy data with the 6 clusters, which I just talked about a second ago, this in the top left is the original decision graph that you would get from the DPC method. And it looks like a bit of a mess, right? It's very difficult to try to assess the true number of cluster centers here and which instances should be centers and should not be centers. And when you overlay the points here, the colors here are actually the colors of the component sets in the couple of slides previous, the task becomes even more difficult, right? If you were to try to actually think about which ones you would want, you need to select the point here in the top right, this point here, these two instances here, this one here, and the yellow one over here, which is a very, very difficult task to do blind, right? And I don't think that you would actually even go towards those instances on the unmarked decision graph. If we look at what happened in the component-wise approach, well, what we see is that the centers are actually much more extreme, right? We can see that the centers are actually projected out much more clearly from the remainder of the data points, right? Which is great, but I'm sure you're thinking that's not a great thing to do, right? Because we've just gone from observing one graph to observing 5 graphs, yeah? Which is a very, very high cost, and it takes a long time to do it. Even though the task within each graph is easier, actually assessing 5 graphs is a very difficult thing to do. So what we need to do is we need to try and zoom in on this line of the algorithm, right? Where for each component set, we're selecting cluster centers manually. We want to find a better way to choose the points which are the cluster centers, okay? We want to try to find a method which does that with minimal individual input and with as little extra computation as we can, okay? So just sort of a take on where we are. We see that separating the data into components improves the discrimination of the centers, but analyzing the multiple decision graphs isn't feasible in any application. It's not a reasonable thing to ask anyone to do. Any sane person anyway. So we have a shared nearest neighbor graph for each component set, which shows us the relations between the instances and describes the structure of the component. We also have centers, which are proposed by the density and the distance values. And if we think back to the allocation procedure, what we see is that when we choose a point as a center, that necessarily defines the cluster automatically due to the allocation procedure. And what we see is that once we choose a center, the cluster defines a partition on the shared nearest neighbor graph. And what we use community detection quality quantities to assess the quality of the partitions that the proposed centers give us. So we're going to use a quantity in CPF called conductance, which is from graph community detection. People might know what it is, but I'll give it a brief introduction to how it's computed anyway. So a CUD on a graph partitions nodes into 2 non-empty subsets, so S and S bar. And the conductance is a quality which is used to assess and compare different CUDs with each other. So the conductance is a ratio. On the top, what we do is we sum over the edge weights which lie across the partition. So these are the instances which lie in one part of the one side of the CUD and the instances which lie on the other side of the cut. We sum all the weights which lie across the partition. We divide by the total weight in the smaller of the two subsets, S and S bar. So if we look at this sort of another stupid example down here, if we consider the partition which separates this cluster here from the remainder of the data set, we see that the conductance would be the sum of this weight, this edge plus this edge, divided by the edges in this cluster here, all of the edges. And that includes the ones which lie across the cut. Whereas if we consider the cut which separates out this point here from the remainder of the points, we see that, well, the conductance of this cut is just going to be equal to 1, because all of the edges in this cluster lie across the component. So the edge weights across the cut are exactly the same as the edge weights in the smaller of the two subsets. So what we would see is that the conductance of the cut on the left has smaller conductance, or is smaller than the conductance of the cut on the right. Yeah. So if we go back to the toy example, which I talked about earlier on, we can see here that what I've done up here are two potential partitions of this component set. Yeah. The first one, which is the one which we got earlier on, which seems quite reasonable, and another one which seems unreasonable, right? One that we would want to reject. If we look at the graphs, right, we see that for the good partition, there's few edges which go across the cut. Yeah, there's only 3 edges which lie across the cut there, compared to, I don't know how many edges which lie across the cut here. And what we see is that the actual edge links here on the good partition are weaker than the edge links which lie across the partition, across the poor partition. Yeah. If we look at the conductance values, we see that the partition which we would want to accept has lower conductance than the partition which we would want to reject. Yeah. And that's something which is common in a lot of works, right? What we're trying to do is find a partition which has minimal conductance. Yeah. And there's a paper by Leskovich and colleagues where they actually develop algorithms to search for minimal conductance cuts over large networks of data. So if we think about where we are, the partitions can be assessed using conductance. We know that conductance is an effective way of assessing two partitions. It can reject partitions which we don't want, and we can get better values for partitions which we would want to accept. But where do we get these partitions from necessarily? Well, the peak finding method ranks, we can get a ranking of the instances, right? What we do is we compute the product of the local density and the distance, and that gives us the extreme points in the decision graph. Yeah. If you look at the plot which I have here, these are them plotted in descending order. So this instance here has the largest density times distance, second largest, third largest, 4, 5, 6, all the way down. These are in order of potential centers as we go through. But to determine, once we have a center, the partition is already defined by the agglomerative assignment structure of the DPC method. Yeah. But what we need to do is we need to find a way to determine, well, how many of these instances here should I consider as a center? And then as a result, how many clusters lie in the given component? So the first question that we need to answer is, does a component contain more than one cluster, right? We can't assume that it does. That's a difficulty in our method. In the original DPC method, you can kind of assume that there's more than one cluster in the data set, which you're clustering, right? But once you've separated things out into component sets, it's not necessarily obvious, it's actually not true at all, that the component set will contain more than one cluster. The component might have done the clustering for you, and you need to find a way to say, no, we don't need to further partition this component. We can't compute the conductance, though, of no partition, right? We can't compare the conductance of a cut versus no cut, yeah? So what we need to do is actually use a heuristic rule that there should be stronger and more common, more prevalent internal connections than external connections across a cut, which we would want to accept, right? So what we do is we kind of do this process of blooming a graph. I'm going to give a little example of it in a second, where we find the value k such that the component set is connected. It's the minimum value of k such that the component set is connected. We compute the conductance of a partition for that value of k, and then increase k by 1 and assess the conductance of the partition then. And what we see is that if the conductance doesn't increase, we want to accept the partition, and if the conductance increases, we want to reject the partition. So let's go back to this. I'm sure you're sick of this by now. This toy example again, where we have the partition which we would want to accept and a partition which we would want to reject. Here, the value k tilde, which is the minimal value of k, such that these component sets are connected, is 7. And we see that the conductance of the partition which we want to accept is 0.025, and the one which we'd want to reject is 0.43. A priori, we don't have any way of comparing this partition versus no partition, and similarly for this one. So this is the process to try to assess whether we want to accept one partition or reject the other one. So when we increase k from 7 to 8, we can see that the conductance values actually move in opposite directions, right? The conductance that we want to accept, the partition which we want to accept, the conductance of it drops because the internal links become stronger as you increase k, right? Relative to the relative external links. Whereas the opposite is true for the partition which we don't see as reasonable. In fact, when we increase k here, the external links actually grow at a quicker rate than the internal links. So what we would see in this, if we were doing this, is we'd accept the partition on the left, but we would reject the partition on the right. So we'll have a method to sort of assess whether there is more than one cluster in a component set. We can figure out, well, how many should there actually be? Yeah, we have proposed centers from the component by the sorted product of density and distance. And what we do is for each potential number of clusters, we compute the maximum conductance of each partition for a cluster in every proposed center. And you can do this up to the number of instances in the component set, or you can set a termination value to stop it. But it doesn't actually have much additional computation required because we've already computed the component set in the, to compute the component, because we've already computed the component set, we have the graph of the instances. So what we're doing is we're just assessing partitions of the same graph. We don't need to find additional k-nearest neighbor graphs, or we don't need to do any sort of searching over the data set. We have all of this information stored in an edge weight array, and we're just essentially assessing different proposed partitions of that array. So if we go back to this again, this toy example again, right? We can illustrate this final part of the center selection. So here I have 3 proposed centers, right? Center 1, center 2, and center 3 here. So we know from the previous example that there is more than one cluster in this component. But how many clusters are there? Well, if we compare the conductance of the partition with 2 clusters, the maximum conductance, it's 0.0247. Whereas if we consider the maximum conductance of the partition with 3 clusters, we see that it's 0.071. What we again want to do is choose the partition which has a minimal conductance value. So we're going to choose the partition with 2 clusters of the partition with 3 clusters, which is exactly what we wanted or exactly what seems intuitive from this visualization of the data. The issue is that the change in conductance isn't a convex quantity, right? So you need to assess it all the way up to a specified maximum, actually choose the minimum value which you want. You can't just keep doing it until the conductance value starts to increase. It's sort of noisy, so you need to compute it all the way up and compute the maximum or the minimum. Can choose the partition which has minimum conductance. So if we zoom out and actually think about the overall method which we have here, right, the computational complexity of the approach is low. If we use a fast k-nearest neighbors method, right, we have, that's an O n log n complexity procedure to compute the k-nearest neighbor graph. There's a method in Zhang et al. 2013, which we use in our implementation to do that. Finding the nearest neighbor of higher local density is another taxing process in the method which we have. So for the vast majority of instances, this is an easy thing to do, right? You have an array of the edge weights and you have a list of all the densities, and you can search in the nearest neighbors to find which point has higher local density. But if none of the nearest neighbors have higher local density, what we need to do is search over the whole component set for that instance to find its nearest neighbor of higher local density, right? There's potential for computational bottleneck here, right? Because that's quadratic computation if you had to do it for all the instances. What we see experimentally, though, is that the proportion of instances which need this broad search is actually less than 1% for large components, and the proportion actually decreases as the size of the component set increases. So compared to other popular density-based methods like dbScan or the original DPC method, our method is more applicable for large data sets. It has lower computational complexity. So all in all, the complexity of our method is O n log n plus n sub c squared, where nc is the size of the largest component set. But this n sub c squared is mediated by that proportion p, which thankfully is low. So just going through some quick experimental results, we compared our approach in the paper to standard methods for mixed data. So variance of k-means, AD k-means, which uses a dissimilarity metric based on co-occurrence of feature values, and GenClust++, which is a genetic k-means approach, which is the only other method which we use, which doesn't require the number of centers to be known in advance. We achieve much better results than these clustering methods and more correct choices of the number of clusters. The reason for some of these data sets is that the outlier detection, the removal of the outliers in the component set process improves the performance of the clustering method a lot. And the non-spherical nature of the detection, the ability to detect non-spherical clusters, is another major boon of the CPF method relative to these k-means based procedures. For these categorical data sets, I included these because they had greatly improved results when the weight W is used. So we just found that was sort of a validation of including information about category frequencies in dissimilarity metrics can actually improve the clustering results which you get. And obviously there's much more detailed stuff about that in the paper. And then for mixed data sets, we see that actually AD k-means performs very, very well for the credit data set, implying that there is some useful information in the co-occurrence of feature values, which might be something to try to incorporate into a dissimilarity metric in the future. What we see is that our method performs much better for the KDD data sets here, which are imbalanced data sets. So we can see that the CPF method is definitely better than k-means or k-means type methods for data sets containing clusters of very different sizes, which I don't think is anything particularly surprising. For large data sets, this is just a subset here. So here we have the cover type data, which has, I think, about 500,000 instances, and the KDD data set, which has over 4 million instances in it. We see that our method has good, well, best, but not very good clustering results. So definitely better than definitely better than the original K prototype approach. And Camilla, which is another semi-parametric k-means method, we see that the Camilla implementation is by far and away the quickest of the three approaches. And the reason for that is they apply really, really strict termination rules on their k-means procedure. So their k-means actually terminates after maybe one iteration or two iterations for these data sets. So even though it's super fast, they don't really get very good results. what was really good was that our implementation, which is in Python, outpaces the implementation of the vanilla K prototypes method, which was also in Python. So we were sort of, about half to a third to a half of the time that it took to run K prototypes, which is sort of a benchmark for clustering speed that we set ourselves at the start. So it was a good result to see. Here's just some stuff about the validation of that proportion P. So we can see that the proportion of instances which require that broad search is low and sort of stuck under 1% as the number of instances increases, which supports the complexity analysis, which I talked about previously. And then there's a small bit about parameter estimation here. We want to do a little bit more work about parameter sensitivity, especially choice of K, the little k here. Determining the components is obviously a vital part in the success of the method. So what we found that that experimental results sort of echoed what's in the literature, that 5 to 10 is a reasonable method, but how can you know what the optimal value of K is before setting off in your data is something which we're thinking about and trying to do more work on. And similarly, for capital K, we sort of matched the other stuff in the literature, that the root n is a reasonable thing to do for this kind of kernel density estimation in the local density step. So all in all, we, just to summarize, we introduced a new clustering method which has subquadratic computational complexity, is able to cluster mixed attribute data, and has superior results to a number of benchmark methods. We have a lot of flexibility in the parameter selection and the choice of the weights W, which can greatly improve the clustering outputs for categorical and nominal attributes. In terms of future work, right, these partitions are crisp, right, which isn't necessarily preferable, but in a lot of the applied work that uses these clustering methods, they take as given these crisp partitions. So that's why we didn't think it was particularly bad to actually generate a clustering method which gives you these crisp partitions. What's nice about it as well is that we do get cluster centers for each of the clusters, which do have a certain qualitative value for a user. And I do think that you could extend this pretty easily to proximity data as well. So that's it. Thanks so much again for the invitation to speak. I hope that was okay. It's great to have a chance to share the work, and I just want to thank everyone at Young ISA again for their help. Thanks so much.
Oh, thank you, Joshua, for the presentation. I think it was great. So the floor is open for questions and discussions. If you want to ask a question or you want to provide a comment on Joshua's work, you can either unmute yourself and just ask him directly, or write it down in the chat and I will read it for Joshua.
Thanks so much.
Hi, Joshua. I have a question. It was a great presentation, by the way. Well done on that. Just to know, you're saying you remove the outliers before applying the method. So how do you is there a way you say that that's an observation is an outlier? You do that in your method?
Yeah. So when we set the parameter K, right, that gives us the shared nearest neighbor graph. What we say basically is any instance which doesn't have an incoming edge is considered an outlier, not in the nearest neighbor of its nearest neighbors, right? Which means that it's likely to be an outlying point. So we remove those points in advance. In the implementation which we have, which is just there at the bottom of the slides, you can actually set as a threshold if you want, not just one incoming edge. You could have any points which have less than 2 incoming edges or less than 3 incoming edges can be removed. That's something which you can set in advance. Mm-hmm. But for most of the work which we found, that actually just removing instances which have no incoming edges is the best way to do it.
Okay. Thank you.
Thanks a million.
Are there other questions for Joshua? So Joshua, I do have one. Can you clarify a bit those weights that you introduce in in your objective function, especially the weights related to the categorical variables?
Yeah, definitely.
So I didn't get, are those weights parameters that you estimate, or are something that you use to just to weight the contribution of those categorical variables?
Yeah, they're things which we use to weight the contribution of the categorical variables, and they're stuff which are sort of determined in advance. So for the weights W, we in the paper proposed 2 different ways that you could compute those. So the first would be the proportion, basically the proportion of category frequency. So if one category is 50% of the values and another one is 25 and another one is 25, then the weights would be those proportions, a half, a quarter, and a quarter. And what you would see is, because you're weighting common attribute values more heavily, you're prioritizing that they get considered together in the clustering. You can obviously reverse that and get the negative log of those proportions to invert it, which is what's used in a lot of document retrieval things, where they'd say that actually rarer category values should be considered as having more informative value and should be considered together. Or you can just set it to be 1 and just say that's something that I don't want to actually think about in advance. Then the weights row aren't things which you can determine as a user. They're computed basically just to ensure that the total expected contribution of each categorical variable is the same as each of the numerical variables. Because we standardize the numerical variables, they obviously have standardized variance, and we need to just ensure that the expected variance of the categorical variables is the same.
So rows are parameters that you would estimate those rows during and have you thought of borrowing ideas from sparse clustering, where you have sparse weights, and that way you would like perform a sort of feature selection within your clustering framework?
Yeah, definitely. Feature selection is something which we really need to think about in this, because, like, you know, there is obviously, when you're doing this sort of unsupervised work, having loads of different features, you're only trying to extract the informative ones out. It's something which we need to think about to actually put into the framework, how to do it. But I definitely think that that's a great idea. Yeah.
That's very good. So are there any other question or comment for Joshua? Okay, so if not, I think we can wrap it up, and thanks Joshua again with a virtual round of applause.
Thanks, Million. Thanks so much.
Thank you very much for presenting your work. It was great.
Thanks so much.
I'll see you all for the next webinar session.
Thanks a million. Cheers.
Thank you very much.
Thanks to everyone at UNISA for organizing it. It was great.
Thank
Bye.
You. Bye all. Bye bye.